The third type of heat transfer is called radiation, and this is qualitatively different than conduction and convection. While conduction and convection depend on uh, mass, on molecules actually banging into each other as a way to transfer thermal energy, radiation transfers thermal energy through the emission of electromagnetic waves.
All right, so the last one that we're going to talk about is radiation. Radiation is quite different than the others because it doesn't involve conduction at all. It doesn't involve those molecules banging into each other and transferring kinetic energy. Instead, uh, at the molecular level, we have to talk about charges. We haven't done that in this class, so be pretty broad about this. But basically, molecules have internal charge imbalances um, because of where the protons and neutrons and electrons are located. And when they move, these imbalances create electric fields between the different molecular particles. Um, as the molecules move around, um, those fields change, and those fields changing and interacting with the other fields and other molecules actually create electromagnetic waves. Okay, what that means is essentially energy starts radiating away from these molecules because of the way they're interacting with each other, and this is called radiation. And it can transfer thermal energy from one surface to another. So here we look at this thermal imagery here, and you can see the different colors here. And hot means warm, and uh, purple and blue mean less radiation. And what this is measuring is basically those electromagnetic waves. This is telling us what temperature these surfaces are, but it's also telling us it's the way this imagery works is it's capturing those radiation waves from this building. And we can't necessarily feel those, but we can detect them with a camera like this. The other interesting thing about a radiation is it doesn't need a medium. Okay, it can transfer heat through a vacuum, and we should be glad of that because that's the only way the sun warms us, right? So space is essentially a vacuum, but we can still get that thermal energy from the sun. So every object radiates emission unless its temperature is absolute zero, and there aren't really anything that has a temperature of absolute zero. So everything radiates. As the temperature of a surface rises, the radiation increases. So you can see here, the flame down here is hotter, right, than the flame up here. And we see that as a different color because of what the spectrum of that radiation, right? So the hotter temperature down here is producing radiation that's in the visible range, and that's why it has a particular color, right? So you move from uh, sort of bluish hues and violet hues this way over to orangish and reddish hues this way. Anyway, so what this is essentially saying is we're seeing radiation coming from this gas, and that appears to us as different colors because of the different wavelengths of that radiation. So radiation at a given temperature has a different wavelength than a radiation at another temperature. All right. The last thing about radiation is what's called emissivity. Temperature has a big role in how much radiation is being emitted from an object, but so does emissivity, and that has to do with the actual surface. Okay, so emissivity can range from 0 to 1, and it tells you how much energy it can absorb or reflect. So black matte objects has a really high emissivity, and it absorbs very effectively. Shiny objects or white objects have a low emissivity. So when you have radiation that hits a mirror, for instance, almost all of it is bounced back off of that surface. But when you're wearing a black t-shirt in the middle of summer, any of the radiation that hits it, that is all that solar radiation, gets absorbed by that t-shirt, which is why it feels better to wear a white t-shirt on a hot day. So what color do you wear when it's a cold and cloudy day and you want to stay warm? Well, we have the same situation that generally if something emits radiation well, it also absorbs it well. Okay, so a black t-shirt would absorb solar radiation, but it's also going to emit the radiation from your body temperature. So on a cold, cloudy day when there's no solar radiation and everything around you is cold, you want to wear something white so that you're not losing a lot of heat to your environment. So these images over here show, in some ways, what's happening when radiation lands on a surface, right? If you have a black surface, a lot of it's going to be absorbed, very little will be reflected. If you have a silver-coated surface, very little is going to be absorbed and most will be reflected. And similarly, if you have a black surface at a certain temperature, it's going to emit a lot of radiation, while the silver one is not going to emit that much. Okay, so now we can turn to a rate equation for radiation. And that rate equation looks something like this. Okay, again, thermal heat transfer per unit time is going to be equal to temperature to the fourth, and we'll get to that in a second, times the area, surface area, right? So if you have a bigger surface area, you can emit more. Your emissivity, and then this sigma, which is a constant called the Stefan-Boltzmann constant. Now the interesting thing about this is that T to the fourth term. What does that mean? It means as your temperature goes up a little bit, the amount of radiation is going to increase very quickly. So if I double my temperature, I'm going to create 16 times as much thermal radiation because of doubling my temperature. T always has to be in an absolute scale, right? And we know that because if the only thing that doesn't emit is something that has a temperature of 0 Kelvin. And so if we put a 0 in here, we would expect that to be 0. Now, this is just for what's being emitted from a surface, but if we want to know how a surface's energy is changing, we want to know not only what's being emitted, but what's being absorbed as well. Okay, and so that gives us this form of the equation down here, and it's telling us essentially what's the difference between what's being emitted and what's being absorbed. So we're assuming here that our emissivity is also telling us how much is being absorbed from incoming radiation. And so if we wanted to know what was going on with surface T1, we would say, well, it's losing this much energy because it's emitting, right? That's why that's a negative. But then it's also going to be absorbing whatever's coming from the outside. So if our surface 1 was 100 degrees Kelvin and our surface 2 was 200 degrees Kelvin, we would expect the thermal transfer to be positive, right? So this number will be smaller and this number will be larger. Again, it's really easy in a physical situation to figure out which direction the thermal heat is flowing because it's always going from the hotter surface to the colder surface. So pay attention to these signs, but then always check your signs when you're done with your question. Make sure that your answer tells you that the heat is moving from the hotter surface to the colder surface. And those are the three kinds of heat transfer: convection, conduction, and radiation.